Hi everyone, I'm Nam from the Batista Lab, and today I would like to discuss on how to implement quantum dynamics and the variational quantum eigensolver on bosonic modular devices. There are several computing platforms that support this, and we chose Strawberry Fields, which is developed by Shenado, a Canadian quantum computing hardware and software company that utilizes qubits, thinking of them having energy levels on a harmonic oscillator, instead of qubits, which has energy levels on an anharmonic oscillator. So this tutorial will show first on how to simulate quantum dynamics in the Strawberry Fields platform by applying a set of optical gates on a given input state, such as shown here. And second, implementation of the variational quantum eigensolver that optimizes the parameters of the circuit so that a desired output state is obtained. So shown here is a Wigner representation of the target state, and on the right is a Wigner representation of the best learned state after you optimize the parameters. So just to reiterate, many quantum computers use qubits and require the use of dilution refrigerators. But photonic quantum computers use Q-modes, they operate on bosons, and they are compatible with room temperature. It has been shown that discrete variable models, just as the Qiskit package developed by IBM, and continuous variable models, such as Strawberry Fields that we are talking here, in quantum computing, they are equivalent. So there are advantages and disadvantages to both ways, but the latter is implementable on the architecture that we have here at Yale University. Like quantum gates for qubits, such as the Hadamard or CNOT, qubits also have analogous gates that allows the transformations so that we can simulate dynamics on the bosonic platform. For example, a coherent state can be prepared by applying a displacement gate to a vacuum state. So here on the right, I'm showing the Wigner representations of the output states after applying a displacement gate. So you can see the place to the right, a squeezing gate, a rotation gate, and a Curry gate to the initial vacuum state. And there are both Gaussian and non-Gaussian gates supported in this platform as well. So, as I mentioned earlier, since we can build a quantum circuit with continuous variable gates that are shown in the slides, so now I'm going to demonstrate on how we can actually implement that. So I have prepared this notebook here. And as you can see, this is a sample program, a very standard program on Strawberry Fields to run it. So there are 4 main steps so that we can run a desired quantum circuit that we build. So the first thing was to declare the program with the required number of nodes. So here you can see that we're requesting 2 modes for the program that we're running. The second thing is that we need to specify the engine backend. So here I'm specifying that I'm using the Gaussian backend. However, since we might be doing optimization later, or the variational quantum eigensolver that I was mentioning, the TensorFlow backend might be better. And the other 2 backends that are supported are the Bosonic and the Fog backend. And it's also important to note that the engine backend is crucial because it dictates the numerical structure on which the quantum states are built to run simulations. And also, there are remote engines that allow cloud access to the Shenado's quantum hardware in Canada as well. So the third step was to define the circuit with the gates, their corresponding parameters, and what modes they act on. So here, I am preparing an S gate or a squeezing gate with parameter 1.0 onto the first mode, Then I prepared another squeezing gate with parameter -1.0 into the second mode. And then I prepare another beam splitter gate. I don't put in any parameters here because they're already default parameters as well, onto 2 modes. And finally, I just measure the outputs. And after you declare the program, you declare what the quantum circuit looks like and the engine backend, then you can run the circuit. So now I'm gonna show how to run briefly a Hamiltonian dynamics. So I choose to start with the Kirkhead oscillator because the Hamiltonian or the system has already been learned by some of the earlier publications of our group. So again, this notebook would be available to everyone after the presentation. So I'm just gonna go briefly through the main details. And I've also included here the links to the publications that I was mentioning here as well. So given this Hamiltonian of the system that we're looking at, then we can decompose or trotterize the time evolution operators into smaller terms that look like this. And then from smaller terms like this, then we can find appropriate continuous variable gates that are implementable on strawberry fields so that we can run the circuit on. So as you can see, the first term over here corresponds to a Kerr gate with parameter R, where R is given as depending on the coefficients that appear here. The second term here corresponds to a rotation gate, and the third term here corresponds to a squeezing gate. And you can repeat this process multiple layers, and the more layers you have, the fewer errors that you also have as well. And so when you run the circuit, then there are a few things to reiterate. So first, to run the circuit, you need to declare the program with the number of modes that are needed, right? So here I'm only requesting 1 mode. Then I pass in the parameters onto the quantum circuit that I was looking for, right? So the 3 gates that we need for each layer are the Kerr gate, the rotation, and the squeezing gate. The order of them doesn't really matter. So you can see here, there's a rotation, a squeezing, and a Kerr gate. All of them apply onto the only mode that we have, right? And then we have the Fock engine backend, and then we just run the circuit as shown here. And so after we run the circuit, then we have multiple tools to analyze our results as well. One of them is to visualize the Huzimi distribution here. So as you can see here, you can actually make an animation out of it. So you can see in this animation, so this is the initial state. It gets rotated, and then it transforms under the effect of the Kerr gate like this. And then it starts to squeeze again here, as you can see. So we can only we can also see the effects of each gate within like the animation as well. And another way to visualize the results. So here we only have 1 mode. So based on the Wigner representation of the output state, we can also do the inverse Wigner transform numerically so that we can visualize the wave function and see how it propagates over time as well. And as you can see, then the blue line here shows you how it actually like propagates over time. and more on this when we get into it later. And so that's for the Kirkhead oscillator that as a first exposure to simulating quantum dynamics. So now let's jump onto a little bit different Hamiltonian that I also want to show you. So again, one of the just to reiterate, when we want to run like dynamics, quantum dynamics for a system given by its Hamiltonian, the first step would be to write the Hamiltonian in terms of the creation and annihilation operators, or in second quantization. And like before, we write the time evolution operator as such, and then we decompose the time evolution operator into smaller exponentiated operators that are equivalent to the continuous variable gates that are implementable on Strawberry Fields. So as you can see here, the first term here corresponds to the beam splitter. The second and third term corresponds to the two Kerr gates over here. And now we're having two modes instead of one mode, right? So here we are looking at this Bose-Hubbard Hamiltonian, right? And so from this characterized time evolution operator, we can build like the corresponding circuit as such. And it's also very important to note that the parameters for each gate in the circuit depends on the coefficients that appear in the Hamiltonian. So as you can see here, J is the transfer integral or the hopping term, and U refers to the on-site interaction potential. And as is, for example, you can see for the beam splitters, they have two parameters, the transmittivity, which is the first one. So it depends on J, the hopping term. T is the time step that we want to simulate dynamics, and K is the number of layers. And the second parameter is the phase angle, which is chosen to be pi/2, so that it fits this first term in the characterized time evolution operator. Right. So let's look into how we can actually implement this. So again, as you can see from this shared notebook again, then first I also declare a program with two modes. Then I define the parameters that are needed and calculated the parameters needed for each of the gates in our circuit. The backend I'm using is like the fog backend. And then to prepare the circuit, so here we're starting with 2, 0. So fog state of 2 in the first mode and the fog state of 0 in the second mode. So we have to prepare that initial state, because if you don't prepare anything, it's going to start with a vacuum state for both modes. And then I prepare the beam splitter gates for both modes, and then define a Kerr gate and a rotation gate on each mode with the respective parameters as shown here. And this is another way of analyzing the results. So after I run this program, I found out that the only outputs available are 0, 2, 1, 1, or 2 zeros as in the fog basis. So how can I validate my my hypotheses? So here I'm printing out the probabilities of getting those fog states. And as you can see, they all add up to approximately 1. And so this means that no other states are observed. And this actually like agrees with all like the particle preserving nature of the Hamiltonian as well. And based on this Hamiltonian, it is also possible to calculate the energy of the output state, or the expected value of the Bose-Hubbard Hamiltonian that we are talking about. So with the formulas that I shortly derive over here and implement them, then the energy for the given values and the parameters and the input states of the output state is around 2.136, as shown here. So I have covered the Hamiltonian dynamics and how to run it until now. So we're going on to the next part, which is to talk about the variational quantum eigensolver. So now let's make a reverse question. Given the quantum circuit architecture or like an ansatz that we know the form, so is it possible to find the parameters for each quantum gate so that a desired or the target state can be obtained? So the short answer is yes, and it's based on a hybrid algorithm called the variational quantum eigensolver based on the variational principle of quantum mechanics, as shown over here. And so it's called hybrid because so the classical part is the optimizer. It's used to improve the guess of each parameter in the circuit and passing them onto the circuit so that the quantum processor will be able to execute the circuit and update the parameters so that like, we can optimize the quantity that or the observable that we want to. So in Strawberry fields, then the TensorFlow backend propagation is supported, and so that means that we can do the variational quantum eigensolver even more efficiently. So that's the basics, and I'm gonna jump in on how to implement that. So to confirm that we can actually do optimizations, that let's start with the examples that we already know the results and see if it works well. So first I'm going to restate the fact that when you apply a displacement gate onto a vacuum state with so the displacement gate has complex parameter, let's say it's alpha, then you can prepare a coherent state associated with alpha. So different from like running Hamiltonian dynamics. So here I don't pass in the parameters for R and phi directly into the displacement gate here. Rather, I choose them randomly from a normal distribution centered at around 0 and pass them into the circuit. And then after I calculate the variables, then I update these parameters for each step. So that's what I mean by optimization. So here we declare that we only need like a one more program, and then the engine backend is a TensorFlow. Again, the TensorFlow is important for optimization. Then I define a circuit with the parameters for the displacement gate and acts on the first mode. And then I use an Adam optimizer with a slow learning rate. And so here I'm choosing the alpha value or the coherent state that I want to optimize to be 1 over square root of 2 plus 1 over square root of 2i, which corresponds to the polar form like this one. So what this means is that we are expecting that if optimization was run correctly, then the value for R should be optimized from like from a distribution centered around 0 to like a number like near 1, and phi should be optimized to around pi over 4. And let's actually like see if it works like that. So here I am maximizing the fidelity of the output state after I run the circuit each of the time with the coherent, like the target coherent state that I'm looking at. And that means I have to minimize the cost function of 1 minus the square root of the fidelity. And so as you can see here, the fidelity wasn't very good at the beginning of around like 37%, but then after it reached like around 10 steps, then the fidelity was already like around like 98.7% already. So that's a decent number for fidelity, as you can see. And let's look at the results as well. So here, R is actually like indeed optimized to around 1. And phi is indeed optimized to around pi over 4, which is exactly what we expected from the beginning as well. And after optimization, we can also visualize the results as well. So shown on the left here is a Wigner representation of the target output state. In the middle is the initial state that we are starting at, the vacuum state, and on the right is the optimized state, or like the output state with the optimized parameters. And so you can see that the figure on the right is supposed to be as similar to the figure on the left as possible. So that's the very first simple example for the variational quantum eigensolver. So now I'm gonna move on onto another example that describes an effect that is known and experimentally proven called the Hong-Oman effect. So basically, if you input two identical photons, each of them into a port of the 50-50 beam splitter with two modes, then both photons always exit in like the same output mode as you can see here. So let's say you shine two photons into this beam splitter. So either they go out up here, or they go out in this direction. For the second and third possibilities, they're canceled out, as shown over here. And symbolically, what this means is that starting with a Fock state of 1, 1, it can be transformed into a Fock state of either 2, 0 or 0, 2. And I'm just going to emphasize that this is only true. This is true regardless of like the phase angle phi, but this is also only true when we have a 50-50 beam splitter. And so what I'm gonna do in this optimization is that I start with random distributions of theta and phi centered at around normal distributions of theta and phi at around 0. And since we here I'm trying to optimize the total probability of getting 2, 0 and 0, 2, then we so since when you add the probabilities and I want to optimize that to around 1, then we should expect theta to be sent to be optimized to around pi over 4, and that's very important. Phi, I don't know yet, but we should expect theta to optimize to pi over 4 because we want like a 50-50 beam splitter. So again, I declare a circuit with two modes. I choose theta and phi randomly from a normal distribution centered at around 0. I pass them into a circuit. So here I have to prepare the initial state of 1, 1 and apply the beam splitter gates with the parameters. And then there's like an atom optimizer was chosen, and I try to maximize the total probability. So as you can see here, it wasn't great at the beginning. It was very low, but after like 8 steps, it reached like 99.9% here. So it's a good number, and indeed you can see then theta is optimized to around pi over 4. It's actually like negative pi over 4, but this shouldn't be like very important because in the description or like the second quantity or the I would say the continuous variable model of the beam splitters, then we're actually using cosine of theta. So the sine of theta doesn't really matter if it's negative or positive. Where phi is optimized to around 0. So we can interpret the results as this. This number 0 isn't like a random number, but rather think of the effect. So the effect holds true for any, as long as theta is pi over 4, which is a 50-50 beam splitter. Phi can be any number though. And since we are starting with an initial distribution centered at around 0, so it doesn't have to be optimized. It can just stay there and optimize the theta value, and everyone's happy after that. So up until now, I have been covering how to optimize and to confirm that our optimizer was like doing correctly. So the next example would show that let's say you don't know this effect yet, you don't know the results yet, but you can also optimize it. So basically, starting with a Fock state of 1, 0, 0, 0, so we are looking at 4 modes here. After I will try to optimize the parameters within this ansatz. So there are a lot of parameters in here. So so that like we can get like the output state as closest to the output, say to the target state of 0, 0, 1, 0 here. So, and we don't know the results for this yet, right? So here, there are, as I was saying, like there were a lot of parameters. You all chose them from like a normal distribution, and then put them into a program, and we declare like a formal program, put them into. So here I apply like a beam splitter gates. A squeezing gate for each mode, then applying a rotation gate, a single mode rotation gates, and then beam splitter gates between the first and the second mode, the second and third mode, and the third and the fourth mode. And this is the input state. And after I try to optimize the fidelity between the output state and the target state, then as you can see, the fidelity at the beginning wasn't good. Like it was literally 0. But like after around like six steps of optimization, it reached like 98%, which is like really good. And after you optimize it more, like you can even reach a fidelity of like 1, like or 100%. However, it is to be noted that if you give me like a random ansatz, a random input state, and a random output state, or like the random target state, then I cannot guarantee that you can always optimize the parameters so that it reach like 100% fidelity. Again, it also has to make physical sense before building an ansatz as well. So up until now, I have covered on how to simulate quantum dynamics and how to implement a variational quantum eigensolver separately. So I'm gonna end the demonstration with how to actually combine them. So here, I'm using the Bose-Hubbard Hamiltonian. So the circuit is shown to you earlier. So, but when I was running it earlier, I was using J equals to 1 and U equals to 1.5 and K equals to 20 to find the parameters for each of the gates in the circuit. Now I'm trying to optimize the value of J and U so that the output state when you run the circuit would have the minimum energy possible. So as you can see here, I'm not using the Fock backend anymore. I have to switch to a TensorFlow backend. As shown here, that one. And so again, I randomly chose the value for J and U and pass them into the circuit as I was doing earlier. So beam splitter gates, 2 mode beam splitter gates, and 2 single mode Kerr gates, and 2 single mode rotation gates. And here I try to maximum or minimize the energy. So I already built functions earlier to compute them, and I try to minimize the energy of the output state. And as you can see here, starting with an energy of around like 2.48, then after I optimize it, it gets to around 1.51. So the progress is shown here. And from that, I was able to find that the corresponding values for J and U would be 0.723 and 1.23, so that the energy is optimized at around 1.51, as I was showing earlier as well. So that's most of the demonstration that I want to show you on how to implement the things on strawberry fields. So now I'm gonna finally present a scheme on, let's say if you have like a Hamiltonian that you want to simulate, then the main steps to simulate that on strawberry fields or like on any like bosonic platform would be first to map that into an N mode bosonic second quantization form. So you can use the appropriate transformations like the Jordan-Wigner, the bosonization, or the Jordan-Schwinger transformations in terms of like the creation and annihilation operators like this. And then you can decompose the time evolution operator based on the characterization of the Lie-Suzuki product formula here with the given error term. And from the structurization, you can find the appropriate continuous variable gates that are implementable on Schwarzschild fields so that you can build a circuit, you can execute it, you can even implement the quantum variational quantum eigensolver to minimize the energy if necessary as well. And finally, since I was mentioning Qiskit, which runs in qubits instead of qubits like Schwarzschild fields earlier, and mentioned them as like an equivalent to Schwarzschild fields, in the notebook that I will provide to you after this presentation, then I also included the main steps on how you can actually implement this on Qiskit as well. So here, again, we are looking at the cat oscillator again. Then basically for this, I also use Q-tip in complement with with Qiskit as well. The reason why I use Q-tip was because I want to construct Hamiltonian, as you can see here, with this code over here. So I can construct the Hamiltonian with Q-tip, and then I pass the parameters, or like I pass this this Hamiltonian and do the trotterization, and pass the parameters onto Qiskit. So from here, I calculated like the parameters, and then I pass them onto this one. So I pass them onto with the QRE as well. So like all the parameters that after I trotterize, it's all included in Qiskit as well. And so I can also visualize the output as well. So as you can see here, then after like a number of steps, then I also do a numerical Wigner transform, and it quite resembles it, not like 100% similar, but it also quite resembles what we had in the inverse Wigner transformation earlier. And I also try to include like an animation after you use Qiskit as well. And as you can see here, so for this one, because I'm starting from a different time frame, so it performs, as you can see here, like the Kerr gate first. So transform with the Kerr gate, and then it rotates, starts to rotate, and then it's squeezing like this, and then it rotates. So it wasn't rotating earlier; it was rotating like at the end. But like the three main gates, even though Qiskit, they don't have the rotation gates, don't have the Kerr gates, they don't have the gates that we have in the continuous variables I was showing you earlier. They have very different gates, but we can also see the effects on the animation of the quasi-probability distribution over time. And so that concludes the presentation that I have today. And thanks so much for listening, and I'll take any questions or feedback that you may have until now.